Hello, my name is Ze'ev. Thank you for joining me for my Applied Machine Learning for Engineering Design term project. The project that I worked on is given an input force height and angle, as shown by the red vector there, finds the optimal truss to support that load. In this case here, the trusses are represented by a 40 by 80 grid of ones and zeros. Here is a sampling from the training data just to see what the trusses can look like. The first visualization that I did was a scatterplots distribution of the training data. We can see here pretty clearly that this is an interpolation problem. As for pre-processing, I rescaled y and theta to be on the same range. The next visualization that I did was a singular vector decomposition of the output space. I found that the singular vectors show high-level features such as truss members and symmetry. Additionally, it doesn't take many of them to explain most of the variance. Another plot that I constructed is the curvature. This is a mapping over the input space of how quickly or how different the trusses are at those points from each other. I did this by fitting the training points to a 180 by 180 grid and finding the difference via a convolution kernel. It's quite noisy, but hopefully you can see some trend lines. My baseline model is a k-nearest neighbors approach to taking the average of the highest d singular vectors of the nearest neighbors within a radius of r. It does perform quite well, but it's clear that the parameters are not optimizable because it works best with the highest dimensionality and the lowest radius. The singular value decomposition did not help here. Next, I generated a 90 by 90 equally spaced grid of trusses and used a Laplacian kernel. I hope that you can see here that the trend lines are much more clear. What these bright lines actually represent is a change in fundamental class of output. The trusses on one side of these lines compared to the other side gain or lose truss members and fundamentally change in class. By also plotting the training loss in the same space, we can see that they follow the same lines. Of course, nearest neighbor averaging method will perform poorly if it tries to take the average of data that is not representative. My final model is a kernel machine. The kernel itself is the sum of two radial basis functions in L and C parameterizations, which I'll go over soon, times a more traditional Gaussian radial basis function in the original coordinates. It performs incredibly well. It enforces sparsity with compact support. While this is generally frowned upon in contemporary kernel learning, because it makes the gram matrix only semi-definite, I found ways around this. The L parameterization is a change of coordinates that more directly addresses the line of action of the force vector. I found that trusses depend more and are more sensitive on where this line of action hits a supporting wall. Before I explain the C parameterization, I want to show you what a Sobel gradient is. The Sobel operator is a tool in computer vision to find the edges of a photo. In effect, it's a morphological gradient or an image derivative over a matrix. The C parameterization is simply applying the same convolution kernels, except instead of over a matrix of pixels, it's on a tensor of data, in this case here, the trusses. By then applying a Frobenius norm, this turns it into a functional. By then taking a morphological integral, which I took inspiration from the Viola-Jones framework for, this builds a one-dimensional space C that represents, in some sense, the Dirichlet energy. In antiquity, kernel learning is trained by inverting the Gram matrix. The Gram matrix is the covariance of how similar is xi to xj for all pairs. This can be very computationally costly because the Gram matrix is not sparse. In contrast, the C-parameterization is a measure of how similar is xi to the overall functional space that generates the trusses. In finding a nearest neighbor average at point A, it would be incorrect to take into account point B, because in between them is a class boundary, a high morphological gradient, which means that they belong to fundamentally different shapes of outputs. The converse is not necessarily true. A and C might have a similar value in the C parameterization, but in the y theta space, they are quite far. That's why the C parameterization is used as a penalty term. This even removes the semi-definite problem in the Gram matrix, because I never have to construct it. The main goal of this model is to avoid the O of n cubed matrix inversion. Constructing the C parameterization is O of n times d, where n is the number of data points and d is the dimensionality of the input space. This is actually far faster than any current kernel method. In addition, all distances are pre-computed with a KD tree in log n time, so it is very fast and very powerful. As far as I've been able to research, this has never been done before. I believe that this is a new discovery. My future research goal is to generalize this for non-grid-like data. Constructing the C parameterization with unstructured data is a very similar problem to reconstructing a 3D image given sparse gradient samples. I hope to be able to further flesh out this technology and hopefully bring it to the world to greatly speed up kernel learning. Thank you.